And so we explained, yeah, okay, so why do all the graphs seem to have this same pattern? And all the graphs seem to have this same pattern. Why is that? Try to get them to give you the explanation. But they should see that, well, when you roll the dice, it makes sense that the fewest or the lowest amount of opportunities occur at these two extremes, because what's the only way you can get a sum of 2? You have to roll a 1 and a 1. That's the only way you can get a sum of 2. Okay, so that doesn't have very many opportunities, right? And the only way to get the sum of a 12 is to roll a 6 and a 6, right? Okay? And so that's not very many opportunities for those to come up. But a 6 or a 7, there are more possible opportunities to get a sum of a 6 than there is a sum of a 2. Because a sum of a 6, you could get what? A 1 and a 5. 1, 2, 3, 5. Or what? A 3. Okay, 1, 2, 3. 1, 2, 3, or a 2 and a 4. Okay, all of those combos add up to 6. So there are more opportunities for you to roll a sum of a 6. Therefore, the probable outcome that you would roll a sum of 6 is going to be higher than a sum of a 2 or a sum of a 12, because there are fewer opportunities here. And we have a nice handout. On the Bioinherent Organization, the TH cheat sheet. So you can see the combos of the dice and the probable outcome there. Okay, so see how the graph goes right like that. You could hand that out to your students. Just make this bigger and hand that out to them. Or you could hand this out to them, okay, which shows the combos for the dice. So again, the only way to get the sum of a 2 is to get a 1 and a 1. Okay? The only way to get the sum of a 12 is to roll a 6 and a 6. Okay? And so that helps. It helps for them to visualize that. And they'll see this in lecture. This graph or this handout here. They'll see that in lecture. Okay? So that's one way that we one example there. Okay? And then if we look at the if we look at the graphs of the flipping the coins, okay, so you ask them, okay, so what are the possibilities that you can get the coin toss? So heads versus tails, okay, and what should our graph look like? And this is the number of times that it came up heads or tails. So what should we get? They should be, okay, with 100, they should be spot on pretty much 50-50, okay? So we ask the students, we go, okay, so what pattern do we see with the heads and the tails? Out of 100, okay, 0 to 100, they should see that it's pretty much spot on 50-50, okay? And if you were to ask them, well, what if we only had graphed the first 10? Would that be different than graphing 100? And it possibly could. You might ask them, did anybody get one of the two for the first 10 in a row? And maybe they will. It is possible to get 10 heads in a row or 10 tails in a row. But the more flips that you do, then the graph should all look like this. So we talk about that. Why are the graphs pretty much 50-50? And because there's only these two choices. It either comes up heads or it comes up tails half of the time. So when we apply this to probability, the larger your sample size, the more opportunities you have, we see that the natural phenomena tends to mirror those probabilities, okay, those predicted probable outcomes. And so, it is possible to get 100 heads in a row, but that's not very likely, okay, and so we should see that we're getting 50-50 there, okay. And then we talk about the roulette, okay, and you talk about the roulette. You go, okay, so how about what you guys got on roulette. Tell me what you experienced when you played, okay? And how does that apply to probability, okay? And so you talk a little bit about the roulette and say, what were your strategies when you made your bets for roulette? And ask them, what were your strategies? Some of them might say, oh, well, I always bet red, or I always bet even, or I noticed that when we were playing roulette, we seemed to get a lot of reds coming up. So I thought red was hot. So I thought I'm going to bet on red numbers. And so this leads us to talk about some misconceptions, some common misconceptions about probability. And so you want to tie in these misconceptions at the end. And one of the first misconceptions is randomness or representativeness, okay? So we'll use the example, we can use the example, tie this back to the coins, okay? So sometimes individuals will think, well, if you think about having kids, okay? Oh, they had 4 girls in a row, so what is the chance that their next baby is going to be a girl? And people will say, well, he had 4 girls previously, so it's probably going to be a girl. When we know that each child is an independent event, okay? And these coin tosses are an independent event. And so when you talk about independent events, like having kids or tossing a coin, the previous roll does not have anything to do with, what happens next, okay? And randomness as well. So for example, if we tie that into letters of the alphabet here, let's say that you have 26 letters in the alphabet, right? Okay? And if we were to ask you to randomly pick out 3 letters of the alphabet, okay, just at random, pick it out, okay, the chance of you picking out A, B, C, or randomly picking out Z, Z, Z is the same, because you're looking at, there's 26 letters, and so there's 1 out of 26 opportunities that you would pick one. And so whether it's A, B, C, or Z, 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 that the randomness doesn't matter as far as how you spread that out, okay? So there is a misconception there about randomness. And then we have recency, okay? So this is more times in here with the having kids, recency. So for example, oh, red is hot.